Good day all. I hope you all are also safe and sound along with your families. I thank you all and appreciate for all the feedbacks and the queries you're putting in through my YouTube and Facebook. That helps me to customize my lecture, my future lecture as per your request and as per your requirements. Today will be my 8th lecture and pouring in with loads of requests and all that. Therefore, I've chosen the topic today for transverse thrust. As I said earlier, the way I have been narrating the whole subject of hydrodynamics is taking a different perception. Perhaps you may understand that this is something out of the box. This kind of innovation I've taken into consideration basically to make you understand in a very simplified manner. I hope I've been managing to succeed somewhere down the line basis your feedback, your likes, your comments and your subscribes. So now, coming to lecture number 8, it's about the transverse thrust. Now when we talk about the transverse thrust, it's basically presently on this lecture or in this lecture, I'm considering a right-hand screw vessel. A right-hand screw vessel where the propeller is turning clockwise. That is going on the head moment. So, I've drawn this propeller which is right-hand screw. On the head moment she is turning clockwise. So what is happening? That's what we are trying to look into it. There is a pressure, high pressure on top and low pressure at the bottom. Now, to make it simplified, I believe whether we are on bulk carriers or on tankers or most of the ships, we all have worked with the centrifugal pumps. So to make the thing more simplified, I'm just trying to ask you to come with me in a hypothetical situation where this is a kind of a centrifugal pump. Now, the propeller I'm saying, just for a few seconds or few minutes with me. When this impeller is turning clockwise, see what is happening. It is creating a force by name of centrifugal force. The centrifugal force acts away from the direction of rotation. So when the propeller is turning in the right hand side, there is a force created in the clockwise direction. Equal and opposite to that is a centripetal force which is coming towards the center of rotation from where the centrifugal force is generating. So, to make us understand, if I say the propeller being as an impeller which is turning on the right side, a right hand screw, it is got a high pressure as it's turning and low pressure at the bottom. On top it's a high pressure, low pressure at the bottom. Because of which the waves are created and equivalent amount of centripetal force is there to equalize this. Now coming to that point, when we talk about the propeller, it's a right hand screw propeller, there is a helical discharge if I talk about the impeller. In other words, in propeller case, there is a helical rotation of the fluid or the liquid is taking place where the propeller is churning in the water. And also there is a differential pressure, there is a high pressure at top and low pressure at the bottom. Now bear in mind, more the depth, more the water pressure. Therefore, once the propeller is fully immersed, let's say when we talk about when we check in our lubricator that how much is the propeller immersion so that the slip becomes 0 or it's negative, it's nullified. But if the propeller is not fully immersed, the slip increases. Now taking this particular concept into account that when the vessel is fully laden or when the propeller is 100% immersed, that's when the effect of the transverse thrust effect can be pronounced. Now, coming to figure number 2, starting from figure number 1 to figure number 2. We see here, as the propeller is turning or churning the water on the right, in the right hand direction, in the clockwise direction, what is happening? There's a strong suction taking place on the port side. This is the ship shape I've drawn. So there's a strong suction of water which is taking place on the port side and a weak suction at the bottom of this. So what is happening? When the propeller is turning, the strong suction is taking on the port side, it's throwing the water on the starboard side, on a right hand screw. On the port side, there is certain amount of suction which is created. On the port side, there is certain amount of suction which is created by virtue of which the water is flooding in onto the port quarter. On the port quarter, the water is getting flooded for the water which is displaced because of the right hand screw. So what happens? On a vessel with the right hand screw propeller churning clockwise going ahead moment, there is a push given here on the port quarter by virtue of which the bow cants to port. In other words, this is the ship what I've drawn here, looking at it from rear, from aft. If I give a push here, the bow will start canting to port, or bow will start turning to port. Now bear in mind, the effect of transverse thrust is applicable on a head moment only when the speed is less. That's the reason I had mentioned the factors which actually govern the hydrodynamics, the mantras, which are not much but can be honed down to few of them. One is velocity, viscosity, density and water pressure. So coming to the point, on a right hand screw, when the propeller is churning in the clockwise direction, going on the ahead moment, the bow will start canting to port. But this effect can only be cited when the speed is less. Once the speed, the engine speed, the propeller speed, the shaft speed is increased, this effect gets nullified because the head momentum is more than the canting moment. But when the speed reduces, this effect can be seen. The transverse thrust for a vessel, right hand screw, going ahead, the bow cants to port. On a higher speed, this effect nullifies because of the thrust going ahead. Same thing I've depicted here also. The same thing I've tried to simplify here. Now you see here, the vessel is going ahead. That is when she is starting from rest. Newton's first law of motion. When the vessel is starting from rest, we will find, as I said earlier, first is the pivot point goes forward from the center. That is, when the vessel is at rest, till it starts moving ahead, the pivot point goes forward approximately 1/4 of the length from the bow. And it settles down because the water pressure what it is getting on the bow, virtually it settles to approximately 1/4 of the length from the bow. Coming to this, let's say the vessel was stopped. This is to explain you again. That's the reason I'm trying to explain you from different points of view, from different angles. So just to make sure that we understand and we are on the same page. So let's say this vessel is at rest presently. The pivot point initially is at P, and the moment the dead slow ahead or the kick is given ahead, the pivot point starts going ahead and it settles down here approximately 1/4 of the length from the bow. And during that point of time, what happens? When the vessel speed is less, she will start canting to port because of this positive pressure. Because again, coming to the same thing which I said in my first lecture, do not forget the importance of the underwater volume of displacement. Like in this particular case, when the vessel is moving ahead, see what is happening. The momentum is gaining gradually as we increase the speed. During that time, a cant to the port is experienced. The underwater volume of the displacement of the ship is getting filled up by the water from the port side. So that's the reason we have a positive pressure here. This will keep going on till such time the speed is increased. Once the speed is increased, all these positives will shift to the bow. They will be approximately in this curve, in this curve. But till such time the speed is picked up, there will be a positive pressure here on this side because the bow will start canting to port at a slow speed on a vessel with the right hand screw gaining momentum. Now, at the same time, see what is happening. There's a positive here also, but there's a virtual negative created here because of the propeller. The propeller is turning or churning the water in the right hand screw. There's a vacuum on the port side. This vacuum is for the water which is getting displaced. That is from here till here. But looking at the shape of the transom, it's curved. When we talk about the ship is like this. It's broad at the midship and gets tapered at stern and at the bow. So I'm talking about at stern. Looking at the stern point of view, the stern frame, the transom. What is happening when the propeller is churning? There's the transom is tapered at the rear. There's a vacuum created. This vacuum is created. One is because of the right hand screw motion of the propeller, and the water is getting displaced. This is helping the vessel to push her on the port side at the transom, and the bow cants to port. This is only applicable when the vessel speed is slow, as I repeated myself earlier as well. But when the speed increases, what happens? This force is not so strong. It gets nullified because of the velocity of the main engine or the propeller. When it is increased, the RPMs are increased. This gets nullified and ship starts going on a path or on a course till such time the speed is reduced. So the effect of transverse thrust is very much predominant, or the predominance of the effect of transverse thrust can be cited only when the ship speed is slow or less. As I'll repeat myself before I go to the next one. As I've shown in the figure number 3, as the speed increases, pivot point from P, from this almost center of the ship, goes to the bow, approximately 1/4 of the length from the bow, and the transverse thrust effect reduces as the speed increases. But till such time the speed is less, see the positive forces are on the port side, and these will keep on, the vessel will keep on experiencing until such time the speed is less and the transverse thrust effect will be predominant. The moment the speed is increased, these all positive forces will shift here and will be laying down somewhere here. That is when the ship's speed is increased. During the same time, as I said earlier, the virtual vacuum or virtual push at the transom, at the stern will be created, which will enhance the effect of transverse thrust for a vessel to turn to port on a head motion. Now coming to figure number 4. When the vessel is going astern, again, initially when the vessel is at rest, the pivot point is at the center. But the moment the stern thrust is given, or the engines are given stern, the P pivot point will go up to L/8 and then will settle approximately L/4 because of the water pressure generated for the ship. When she is drawing astern, the water is moving forward, ship is going astern. On a right hand screw, the bow will cant to starboard as per the property. In other words, if I change the direction of these arrows, that is here, if I change the direction of these arrows, that is when the propeller is moving anti-clockwise, the whole thing is reversed. It's a mirror image of what I've shown here. It's absolutely the mirror image of what I've shown here. Now, what is happening when the vessel is going on the stern thrust? The water is going forward, vessel is drawing aft, the pivot point is coming to 1/4 of the length from the stern. At the same time, the underwater volume of the displacement, again, what I explained earlier, what I also explained here, plays a major role. When the propeller is turning anti-clockwise, the bow is trying to cant to starboard, the underwater volume of displacement is getting displaced. The water which is coming from the starboard side is filling up the void as the vessel is turning to starboard. Same thing what happens in the forward motion. When the vessel is canting to starboard, the positive force which are generated due to the vessel's cant to starboard, the water is getting filled up here, the positive on the starboard side going astern and negative on the port side. So coming to this figure, the vessel is canting to starboard on a stern thrust. Now, stern thrust, the output is approximately, this is with experience, is approximately 50% of the ahead thrust. In other words, the stern power, which many times the pilots also ask the captain, what is your stern thrust power? Some ships have 50. I've been on few ships which has about 60 plus approximately. But on an average, we can take approximately 50% of the ahead power is the stern power. In other words, what we can give the RPM at the stern thrust, the speed effect will not be much because of the stern thrust power when the engine is reversing. So, what is happening as we have shown on the figure in the figure number 4, that when the vessel, the bow is canting to starboard, there is a positive pressure because of the underwater volume of displacement. The water is coming and filling up this void as the vessel is turning or canting to starboard. And the water is receding on the port side. So, positive created on the starboard side, negative on the port side. At the same time, coming to the centripetal force. Now, the centrifugal force, which is actually when it is turning in the reverse direction, it's sucking the water from the starboard side and throwing it on the port. When the vessel is going astern, the propeller is moving anti-clockwise. It's sucking the water from the stern and throwing it on the port. That is, sucking the water from the stern starboard and throwing it on the port. That is port quarter. So, because of that, when the vessel is going astern, the vacuum is created on the starboard side, you get a push. You get a push on the starboard quarter, and that push also helps the vessel to cant to starboard. It's something like this, that I've connected a tug here and I'm asking the tug to pull, to push. That and whatever is the fulcrum with that, she's swinging to starboard. So, the vacuum which is created on the starboard side is acting as a kind of a virtual tug push, which is facilitating vessel to cant to starboard. What is shown over here, that positive forces are here, vessel is turning on an anti-clockwise direction and the suction is created on the starboard quarter and positive pressure on the port quarter as what I've shown you here. Because of the underwater volume of displacement, the positive is on the at least up to 1/4 of the length from the stern. So the positive forces are approximately 1/4 of the length from the stern. To make it more clear, I depict it over here. The positive forces experienced by the vessel going on onto the stern movement is approximately 1/4 of the length from the stern because of the underwater volume of displacement. As the vessel is turning to starboard or canting to starboard, the water is getting filled up. Likewise, a virtual positive force is also created on the transom, on the port side. Because when the propeller is turning anti-clockwise, the virtual positive forces are generated on the port quarter, which is also facilitating because the water is getting filled up as the vessel is canting to starboard. So whatever the vacuum is created because of the underwater volume of displacement is getting also filled. Now, when we talk about this, the effect of transverse thrust can be seen when the effect of squat is not very high. In other words, in the water of lesser depth, obviously, the water pressure will also be less. At that point of time, you must have realized that if in a narrow channel fairway, when the stern thrust is required, or when it is required to cant the bow at a shorter time, normally the pilots ask for a tuck. It is something similar when we are going alongside. We have the property of transverse thrust, but it's normally not very much pronounced because I'm talking about in shallow waters. In deeper water, the water pressures are high, the effect of transverse thrust are very much pronounced. So, I hope I managed to explain on this particular topic of transverse thrust. You guys have any doubt, any queries, please do not hesitate to ask me, and share my YouTube channel Marine Quest Solutions, as well as subscribe it. Same thing is there on the Facebook. Thank you very much. Good day.